So association rule mining is a commonplace technology that we, even though may be unaware of from the name of it, but we experience it on daily basis. Especially when we go to market, you see every now and then the application of association rule mining in interesting ways. Have you noticed when you go to a market after some time, like after 1 month, the arrangement is a little slightly changed? If you keep going on regularly, you won't notice that change, but markets rearrange their items to sell based on what is being sold together with the other items. So it's very common to find flowers and chocolate being sold together in a particular season, right? Which season would it be? Around the
February.
Valentine's Day, right? There are some seasonal factors and some information is coming from us. The way people are buying things, market reacts to that pattern of buying. They call it market basket analysis. So looking at the basket, they rearranged so that people buy more. It's very common that if you go to market and you don't have a list of items with you, you bring more than you needed, right? Even if you have a list of items, you pick one or two more things. So what's going on there? Market arranges items in a way that they're put together. Items bought together are put together so that you get convinced and you do some pop-up shopping. You also get special discounts on items that you don't need. How does market knows that you deserve a discount? For example, if you go buy black pair of pants and you are checking out, you may get a discount on buying the belt with that pants. Why? Because market knows through association rule mining that people who buy pair of pants also buy a belt with it. It's very obvious, but sometimes you get to see non-obvious links as well through association rule mining. How does market sends coupons for special offers? How do they know what we need? Not only from our own buying patterns, market also learns and predicts about our behavior from learning about other people. They don't know about us, they don't have history of about us, but they know that we are similar to some people based on certain criteria, and then they send coupons, special discounts, arrange their market items in a way based on association rule mining, and famous name is market basket analysis. At the core of this technique is these two things. X leads to Y. So if we know X, we can predict that Y will happen. On the left-hand side of this equation, we can say X is the antecedent. On the right-hand side, whatever is there, we call it consequent. In an association rule, we discover antecedents that lead to consequence. We are going to learn today how we can extract these rules from a transaction database or a large database where we have tons of information. We don't know which one is more interesting or less interesting. So that's it. There is the association rule is going to look like this. X leads to Y. The items in X and Y together are going to be referred to as item set. So if somebody buys milk, they are also going to buy bread. And if somebody buys bread, they are also going to buy milk. If that is a rule, how can we be sure of that rule? How do we measure that an association rule is worthy of paying attention and spending money on? Other than these examples, we can act as a market space investment agency or urban planning government agency. For this particular problem where we look at 6 different locations, in these locations, the market space is occupied by these businesses. For location 1, we have barber, bakery, convenience store, meat shop, fast food. For simplicity, we are looking only at 6 transactions, but we can consider them as 6,000 different locations. And we want to learn if there is a business, for example, flower shop, what other business is missing that can come in this market and make some good income. So your association rule mining application extends not only from just market basket, but into investment and business portfolio regime. So let's say we have an association rule X leads to Y. X is fast food and bakery, and Y is convenience store. The left hand side I mentioned is going to be referred to as, we are going to call it the antecedent, and right hand side consequent. Now, if this is the rule, how do we measure the goodness of this rule? There are some numbers. First is support. Support is very interesting, very simple measure that gives us the fraction of locations that contain both X and Y, or fraction of transactions. We call it probability of X union Y. So if we look at this small database, fast food, bakery, and convenience store, they come together in one market, in one location, 2 times. So total locations are 6. So support for this particular rule will be 2 divided by 6, 0.33. The other number we are going to look at is confidence. How often items in Y appears in locations that contain X. It's a conditional probability. Probability of X union Y divided by probability of X. Here, we can see that X union Y's probability is 0.33. However, fast food and bakery, which is X, the antecedent, is coming together at 3 locations: fast food, bakery, fast food, bakery, and fast food and bakery. So 3 out of 6 locations, the antecedent X is co-occurring. So probability of X is 3 divided by 6. So taking this ratio, X union Y divided by probability of X is 0.66. These 2 numbers are at the core of measuring the goodness of any given association rule. Would you like to? We are looking at the 2 important measures that we can use to compare association rules. For now, we are looking at an example association rule that says that wherever we find fast food and bakery, the antecedent, there will also be a convenience store. So how good this rule is, we want to measure it. So there are 2 numbers that we calculate based on their frequency of co-occurrence: support and confidence. Support of a rule is calculated as probability of X union Y, the number of times these 3 items come together in a location divided by total number of locations. In other words, fraction of locations that contain both X and Y. So we can see fast food, bakery, and convenience store come together in location number 1, and then location number 2. All other locations, we don't see fast food, convenience store, and bakery coming together. So the probability of X union Y will be number of times they come together divided by total number of transactions or locations, which is 2 divided by 6. So the support for this association rule will be 0.33. The other
Okay.
number that we use to measure the goodness of an association rule will be confidence. Confidence is probability of X union Y divided by probability of X. X union Y is probability we just calculated, 0.33. Probability of X will be zero point 0.5. X is fast food and bakery, bakery, fast food, bakery, fast food, bakery, and fast food. Three locations, they are coming together, divided by total number of locations. 3 divided by 6 is zero point 0.5. So the ratio of this number divided by this number give us the confidence about the rule. So these two numbers are at the core of evaluating association rules. For this particular example, we can use it to open a new business. Let's say you want to open uh, a, a business and you have a couple of options. So in which location you will have good investment, wherever there is a good rule. So fast food and bakery and convenience store, they come together with good support and confidence. In that case, if some location don't have convenience store but there is a fast food and bakery, then you can invest in building a convenience store there, because in other locations that particular business is coming together with fast food and bakery. So this is this can be one interesting application of discovering the association rules. The other application could be that you can be an urban planner. You are government and you want to design markets for different locations. So based on the association rules, you can design better and better markets.
Okay, got it. So in that case, Professor, is there a specific value above which it will be considered better or a good number, and under which it will be considered not a good one? Like any specific values for
This
support or confidence?
this is a very important and good question. So it's going to be a subjective number. For different problems, we will move this threshold to, let's say we want to have only 0.95 support association rules. In that case, we will have less rules. If we relax that condition, we will have more rules. So depending on the application, what we want to do with the association rule, we will change the threshold. If we increase it, there will be less rules. If we decrease it, there will be more rules.
Okay,
But
got it.
the higher
Thank
the
you.
better. Higher the support, higher the confidence shows that the rule is very good and we can put more investment on that, or we can act more quickly according to that rule. Rahil?
Yep.
Yes, Professor. So, my question is association rule mining, and is it an algorithm or it is just a logical technique?
Well, for now, we are looking at just the application and the numbers that we use to evaluate these rules, but how to discover these rules from a large database, we need algorithms for that. We cannot do manually.
Okay, so it is like a technique, and we use our uh, like AI algorithms, like decision tree and stuff, to apply on it. Am I right?
We are going to learn the specific algorithms today that we use to discover association rules.
Okay.
But very interesting observation, that word that you said, it's very much similar to decision tree. For example, you can convert this association rule into a decision tree. Wherever there is fast food and bakery, there it will be a convenience store with the support 0.33 and confidence 0.66. If the consequent is just one item, then another association rule looks very much similar to a decision tree, but we induce decision tree with a different algorithm than what we have for discovering association rules.
Okay, got it. Thanks.
And you can also find a parallel between confidence and accuracy, by the way. The accuracy that we use in evaluating classification algorithms, confidence is very much similar to that. Other measures based on support and confidence that we just learned are coverage. How many number of rules are there? So in X, we have some items. In Y, we can have some items. Together, they are coming in how many transactions or in how many locations or how many records. This is going to be called the coverage of association rule. Divide this count by number of total transactions, we get support, right? We can also use antecedent support to select some rules, which is only the probability of X. The confidence, which is in classification, we learn it as accuracy. In AR, we call it confidence, is the ratio of your support divided by antecedent support. Probability of X union Y divided by probability of X. There is another related term, baseline confidence, which is the probability of consequent. How often the consequent is observed in the database. So in Y, if we have 3 items, and we will scan our database and see how many times those 3 items come together. Divided by total number of items in the database will give us baseline confidence. Very related terms, probability of X antecedent support, probability of Y baseline confidence. You can take a difference between the confidence of the rule and baseline confidence. It will give you a number, confidence difference. Or you can take a ratio of both confidence difference and confidence ratio. They both are used to detect very uncommon but useful rules. All right, so ratio and difference are useful measures, but we use them after we are at the end stage of our predictive analytics for association rule mining. In the beginning, we use support and confidence. All other numbers are kind of cousins of these two, but we use them later. In the first step, we are going to rely on support and confidence. Now, we are convinced till now that these association rules are useful. They can let us design our market, launch some marketing campaigns, and send some coupons to the prospective customers. And when we watch, let's say, Netflix, you always see the related movies that Netflix proposes that since you like this, you are going to like this one as well. If you are watching YouTube, you often get recommendations, right? If you are on LinkedIn, you often get recommendations. If you are on Facebook, you get recommendations. This can be a good friend. This can you might like getting in touch with this person. How does these companies know so much about us that very often those recommendations are useful, very much relevant. They are not irrelevant, right? One of the core engines behind these applications is association rule mining. And we learned how we measure the goodness of an association rule using these key numbers, support and confidence. So far, so good?
Yes, Professor.
In that case, if we are clear for and enough motivated, then we can look at an interesting aspect of these two numbers. The same database, if we look at this association rule, can you confirm that the support is 0.33, but the confidence is 0.66? Actually, we just calculated that in previous slide. How about we change the configuration? We say convenience store and bakery are the antecedents and the consequent is fast food. Now the item set is same, but their arrangement is different. Now convenience store and bakery are predicting that there is a space for fast food. How much support for this rule will be? 0.33. And confidence is not going to be 0.66 because why it is 0.5? Because the confidence is calculated based on probability of X union Y divided by probability of X. Now X is different here. Convenience store and bakery. Convenience store and bakery are coming together differently than fast food and bakery. That affects confidence. Another arrangement, fast food convenience store, how good they are to predict that there is a space for opening a bakery business. This time confidence will change again. Another and another. So you can look at the last association rule and can you explain why confidence is 1? Nishit?
Uh, so let's say if we apply the formula, Professor, probability of so it will be probability of x divided by probability of x. That's why it's 1.
It's the formula is probability of X union Y divided by probability of
Okay.
X. So X union Y is 0.33
Okay.
and very interestingly in probability of X is as well 0.33. You can see fast food is coming in 3 locations.
Uh,
It's coming in 4
so it's
locations, Professor.
4. So
1,
4 divided by 6 will
2,
be
3, 4. Yeah, 4 locations. So 4 divided by 6 is 2 by 3.
0.66.
0.66 and so this is a typo. This is going to be a different number,
0.5.
0.33 by 0.66. So it's going to be 0.33 number. So we now understand, and we found a mistake as well in the calculations here, how to calculate the support and confidence. But the items are same in each item set. Same number, same set of businesses, but if we change their configuration, the consequent is different, antecedent is different. In that case, observe that support and confidence can be different. And an association rule is kind of a binary division of the item set. So we divide it into 2. Left part becomes antecedent, right part becomes consequent. And third, support can be same, but confidence can be different, right? So the purpose of support and confidence is to evaluate association rule, but they can play different roles and they can be different. So for all these rules, support is identical, 0.33, confidence is different. So therefore, when you try to select association rules out of 100 rules, you want to select best 10 rules, you can use different numbers for support and confidence. You can say, I want support 0.9, I want confidence 0.6, right? So both numbers need not to be same. Recap. We know association rule mining is interesting and useful. We know how to compare different association rules using support and confidence, and we learned how do we calculate these two numbers as simple probabilities of the item set. Their relevant numbers were antecedent confidence, etc., ratio of the confidence, and difference of the confidence. They all can be used in finding better and better association rules out of hundreds of rules. Which ones to act on? We will use these numbers to filter and get the best ones out. But how do we actually get these rules? How do we extract? How do we convert this database into these rules? We need some technique now. The databases are not like 6 transactions like that we deal with. They are huge numbers. So first thought that comes to our mind that you may ask is, let's use a threshold. So whichever association rule is better than that threshold, we keep it. And let's use a confidence threshold. And that is quite obvious. We are going to use these two numbers, and there will be a two-step approach. First step, we are going to generate an item set from the database. Wherever the item set's support is greater than a given threshold, min support, we will keep those item sets, and from those item sets, we will generate some rules and keep high confidence rules from those all possible rules. Now, you can imagine this problem can get easily out of hand because it's computationally expensive if there are millions of transactions. For only 6 items in our database, there can be this many item sets. 2 raised to power d, where d is the number of unique items in the database. We have A, B, C, D, E, 5 items. All possible combinations of these items look like a lattice, right? So this lattice diagram let us visualize the scale of the problem that we are dealing with. How are we going to select, for example, A, D, E is better, or B is good, or A, B, C, D, E? There is an interesting rule to find out of 2 raised to power d possible item sets, which one is interesting and which one is not. But let's dig a little deeper into the numbers that we are dealing with only for this database. If we want to calculate the complexity, how many number of transactions we have? 6, right? We have 6 locations. Rangita?
Yes.
How many unique number of items we have in the database? There are 20.
20.
total possible number of item sets that we can create with 20 items is 2 raised to power 20, which is, oh my God, is it a million? Over a million item sets. And in that case, the complexity of the algorithm, if we want to find the interesting ones, interesting connections in this small little database will be humongous. N multiplied by W multiplied by M operations are needed. So to the order of NMW, it's a huge problem. Even for a small database, we can see how many times the computations will run. This million multiplied by 20 multiplied by 6, around 100 million, right? Operations. So we need an algorithm, a smarter way to find the good information about the association rules. Are you with me? Do you appreciate the size of the complexity that if we do it like without an algorithm, just pick all possible items, sets, and their rule and check their support and confidence, we are going to do this NMW times. N number of transactions, W number of unique items in the database, and M is 2 raised to power unique items. It's a huge number of operations. Visually, you can see the more the number of items, the number of rules, possible rules that we can extract are exponentially increasing. For only 10 items, we need 10 raised to power 4 multiplied by 6. We can have this, we have to evaluate this many rules. So out of this, 10 item database, there may be 10 or 20 good rules that can benefit a business, but we need to evaluate tens of thousands, which is, not computationally efficient. So to reduce the complexity, number one, we need to reduce number of candidates, M, reduce number of transactions, and reduce number of comparisons. If there is a way that we can reduce these numbers, we will reduce what? The complexity. There are two options. Either we use efficient data structures, or we need to match every candidate against every transaction. No need to match if we can find efficient data structure and an algorithm. So we will reduce the complexity to a high degree. Algorithm number one is based on this principle. For all X and Y, X is antecedent, Y is, let's say X is an item set, Y is another item set. If X is subset of Y, then support for Y will always be greater than support for X will be greater than support for Y if they are the subset. Visually, you can see if this particular item is infrequent, DE, then all the items that have DE in it as a member will also be infrequent. This is what the a priori principle is saying. So when you find DE to be infrequent, D is not interesting. How do you measure not interesting? Using support. The support for DE is less than the threshold that you want. In that case, all the supersets of DE, BDE, CDE, BCDE will also be infrequent, so you don't need to check them. So you save all the operations, 1, 2, 3, 4, 5, 6 operations. You don't check them because their subset is infrequent. Their Superset of DE will be uninteresting. You don't need to check based on a priori principle. So what can happen conversely? The inverse of this rule is that if something is frequent, for example, BDE is frequent, it is interesting, the support for BDE is more than the threshold, in that case, all subset of BDE will also be frequent. So you can, if you check BDE, you don't need to check BE, BD, D, E, B individually. You can just, by virtue of a priori principle, you will know that BDE support is good, so their subsets will have better support. So this a priori principle we can use into an algorithm to reduce the complexity and the number of operations we are required to perform to extract association rules. So step one, we did what? Generated item sets. We visualized them like this, like a nice lattice graph. Now, step number two, we are going to create association rules from those item sets. So both steps require a lot of computational operations, and we are trying to reduce them using a priori principle. Yes, Nishit.
So, Professor, I have a question. In order for us to use this principle, will we have to first of all calculate the
Sorry, I lost you.
can you hear me now?
Yeah.
Yeah. So I was just asking, in order for us to use this principle, will we have to calculate the support of each item in our data?
That is what we are trying to avoid. If we want to avoid, we need to use this a priori principle. If we go ahead and check everything, then the complexity is humongous for generation of item sets, and then for checking the support and confidence of individual rules, there are so many operations to the order of NMW. So we want to reduce those, right? So first hint that I'm giving you is that we can use this a priori principle, which will, for example, if you know BDE, that is, if you use BDE, if it is frequent, you don't need to check BE, BD, B, D, and E, because by virtue of a priori principle, they will be more frequent than BDE. Similarly, if you are checking the support for DE and it's not interesting, DE is infrequent, then you don't need to, DE item set is infrequent, so you don't need to check BDE, CDE, all the supersets. So this is how we can reduce the number of operations using a priori principle. Everybody with me? Arushi? Rangita? Yes?
Yeah, Professor. So basically, in order to determine the frequent item set, we have to use the rule, which is the support is greater than or equal to minimum support. Is that how we determine the frequent set?
Well, for support and confidence, we need to have a rule. But before having a rule, we need to generate item sets. So for generating item sets, we are trying to generate less item sets, and we use just frequency there. We use support and confidence for when we have rules, we will calculate support and confidence there. But the first step is generating the item set. Even at that point, we can come across with a huge number of things to check. Instead of checking everything, we can use a priori principle to reduce the interesting things in interesting item sets. So we can say our interesting frequency is, let's say, 50 or 10 or 100. So we want to filter out all the item sets that have less frequency than a threshold. 50, you will give that, or 2, let's say. And all the item sets, if their subset is infrequent, their supersets will be infrequent as well. If their superset is frequent, like this, BDE, then subsets will be more frequent. This is what a priori principle is saying. And we are trying to capitalize on this principle. So step 1, generation of item set, we will use a number, threshold, frequency. Any item set having frequency above this threshold is interesting. On step 2, we will generate association rules by binary division of those interesting item sets, and we will use support and confidence for those rules. Interestingly, both support and confidence and the frequency that we are using to filter out item sets, they are arbitrary numbers. So frequency can be 2 or 3, and support can be 0.5 or 0.6. Nishit? Sorry, Rangita?
Yeah, I think I'm getting it. Yeah, okay.
Let's look at an example to apply the concept of a priori principle, and the algorithm will now look like this. First, we are trying to reduce the number of candidates. How many, let's say, transactions we have? We will look at that. All possible candidate sets that can be generated from this number will be n C1, NC2, NC3, NCN, all summed together. But we don't need to generate this many sets. If we use minimum occurrence-based filtering, the algorithm will start with 2 variables. We will say M is 2, L is 1. L is the length of the item set, and M is frequency. So while L is less than number of N is total number of items in the database, we will scan the database and create a list which will have the frequency of each item in that list in the database. If there are no candidates in the list, we will break out of this while loop. Otherwise, we will filter all the candidate sets with less frequency than 1 and create a new candidate set of length L plus 1 from the list. Visually, same database. In the first iteration of the while loop, we scan the database. Our L is 1 here. So for every unique item, the item set length is 1. We count their frequency. So barber shops, there are 2 in the database. Convenience stores, 3. Game shop, 1. Sweets shop, 1. So we create, this is the first list that we get from the first iteration of this algorithm. Now we filter all the candidates with frequency less than 2. So M is less than 2. When we filter these, we are remained with only barber, bakery, convenience store, and fast food. In the next iteration, we will create pairs of these to create L2. Now the length of the item set is 2. So we create pairs. For 4 items, there will be 8 pairs. So we again scan the database and calculate the frequency of each pair in the database. So barber and bakery together, they are coming at 1 location. And then for the next iteration, for the filtration step, We see which one of these is less than 2. We filter that out. So the interesting item sets are now bakery, convenience store, bakery and fast food, convenience and fast food. They're based on their frequency. So we keep going through this loop as long as we reach to this limit. So the number of items in the item set are equal to the total unique items. And we end up with only the interesting item sets. Then we can see the support for bakery as antecedent, convenience store as consequent. So we can then do binary division of these interesting item sets. And this simple process will reduce the number of operations to maybe 100 times less than if we don't use this algorithm. We have to do to the order of NMW complexity. So huge number of operations we need to check. But here we are reducing through this simple algorithm. This is called a priori algorithm for discovering association rules. Now, even though it looks much better, but do you see any downside for this algorithm? For a huge database, number one, we need to generate frequent item sets. Somehow, if we can avoid this step, the algorithm or the technique will be much faster. Number two, we need to do database scans n+1 times. So if n is your length of the interesting item set, which can be 10 or 100, let's say if it's 100, you need to scan your database 101 times. Scanning the database is still not cheap operation, right? You need to check all the database to count the frequency of the interesting item sets, which is, if it's a huge database, big data, an expensive operation still. So we will look at now another algorithm that avoids both costly database scan operations, and we will totally avoid candidate generation. It represents your transaction database into a highly condensed but complete format for frequent pattern mining. That's why it's called FP growth algorithm, frequent pattern growth algorithm. There are 3 steps. Let's consider this small database again. In step number 1, we will scan the database only once and find frequent item sets of length 1. So in here, all unique items we create in this table, header table, F, C, A, B, M, P. These are the unique items in this database. And the step 1 gives us their frequency. In this column, we have frequency of F, C, A, B, M, P. In the third column, we have a node that leads us, for example, in the I will explain this in a moment, but after we create the frequency column, we do step number 2. We order frequent items in the frequency descending order. So for this transaction, I is not interesting because it has less frequency. Our threshold is 2. So we will drop I, we will drop G, we will drop D because they are less frequent in the database. So we order the frequent items after filtering the uninteresting ones in descending order. So F, C, A, M, P. This particular transaction becomes FCAMP. This transaction becomes FCABM, and so on. Are you with me?
Yes.
In the step number 3, we scan the database second time, and this is the last time we scan the database. We construct an FP tree, frequent pattern tree. This construction is interesting. How do we do that? Let's look at each transaction one at a time and see how this tree is constructed. First transaction, we take FCAMP and we create a branch in the database, in the tree. So to the root of the node, we put the first item and the frequency of that item. C, A, M, P. Till now, we have come across FCAMP only once. That's why this frequency is just 1 at transaction 1. And then we put the address of this node in the head column of the header table. So header table will lead us to the leftmost node in the tree. For the next transaction, we have FCABM. So we check in the tree, do we have F under the root? Yes, we increment the count. Under F, do we have C? We increment the count. Under the C, do we have A? Yes, we increment the count. Under A, do we have B? No. So we create a new node and put the address of that node in the header table and put 1 here because this is the first time we are seeing B. And then M. After B, we check if M is there. No, we put M under B. A link is missing here, but after putting M under B, we create a link to the existing M. So this dotted line shows the other occurrence of M in the tree. Next transaction, FB. We will check, do we have F under the root? Yes, we increment the count. For B, do we have B under F? No. So we create a node B and put the address of this node in the previously recorded node in the tree. Will you help me do this transaction, CBP? What shall we do for this transaction, CBP, to put into the tree? We will check, do we have C under the root node? We don't have. So we will create a node C and put the address of that node in C. Under the C, we don't have B, so we will create B under C and put the address of B here. And then under B, we will put P. P, we already have an existing node in the tree, so we will create a connection to P here, like this. Similarly, FCAMP, for the last transaction, we will have our complete tree like this. After having this complete tree, did you notice that FCA incremented FCA counts, and then M and P became 2 and 2. So look at the header table now. You have in the one column all unique items. In the next column, you have all the frequencies. In the third column, you have the addresses. So if you want to find F, where is F? There are 4 Fs. You will go in the tree here. Where are M's? So you will go 2M here and 1M is here. This tree can wonderfully help us find the association rules. Based on this tree, we will create a conditional pattern base. A conditional pattern base is unique items in one column and the pattern base in the other column. So look at this. If we see C, for this C item, we want to find the pattern base. We will check the node that is C is child of, and F 3 times, as many as the count of C are coming together with F. For A, we will look at A, and FC 3 times is the conditional pattern base. For B, 1B is here, so FCA 1 time is the conditional pattern base for B, and another B is here, C, coming with C. Another B is here, coming with F. So conditional pattern base is going to be used to create your rules. So from conditional pattern base, you can now filter out based on the frequency. CB1 is not interesting. You are interested only in things that are more than 2. So you can say wherever you find P item, you will also find C 3 times. Once in this transaction, once in this branch of the tree. So these are the rules that you extract from the conditional pattern base which come from this tree, and using this interesting algorithm, you reduce the number of scans to 2. Maximum 2 number of scans in the database, and there is no item generation involved. So in this sitting, we learned association rule mining, the concept, applications, and how they are running the engines of modern AI enterprises and predictive analytics. The challenge there is to generating number of item sets, and then out of the interesting item sets, generating and checking the support and confidence of the rules. We looked at a priori algorithm to reduce that number, and then even better algorithm, FP growth algorithm, that further makes this process more efficient by reducing number of scans and avoiding generation of item sets altogether. So I will stop here and invite any feedback or questions and comments from you regarding association rule mining in general and specifically to these 2 algorithms.